Hello, welcome to lesson 7 of topic 4. In this lesson, we're learning about two-source interference. First, I'm going to show you my setup called the ripple tank that I will use for some of the demonstrations at the beginning. The ripple tank is a motor, which you can't see right now, but you will in a minute, connected to this controller where I can adjust with this knob the frequency of oscillation. That determines how fast the motor is turning, and that determines how fast whatever connected to it is vibrating. There is water in this tank, and if you look at the bottom, because there's light above, we can track the shadows, which actually show us the wavefronts. So let's see. These are little knobs to make point waves. In this setup, I have a ruler connected, so there's the water. This is what I use to connect my phone for recording, and that's the shadow, as you can see. That's the ruler connected to make plane waves, and that is the wavefronts in slow motion. You can see the ripples in the surface and the shadow of the wavefronts. So first I'm putting in a plastic piece to change depth. When the depth of water changes, water waves refract and they move more slowly in shallow water. If you look at the shadow of the wavefronts, you can see that the wavefronts are getting slightly closer on the shallower region, and this is showing you the circular wavefronts. So let's begin. There are 2 point sources and they're generating circular wavefronts at the same time in phase. Now I'm increasing frequency. Observe what you see in this region. Let's explain what happened. So there's a simulation which I can use to demonstrate one source here and one source here. Plane wavefronts will arrive from the left, and from these 2 points they will act like 2 point sources, and they will interfere, form an interference pattern, and we're going to see what happens on the screen over here. They are approaching the screen. Before they do, actually, I want to show you what's happening here. Each of these wavefronts, as you know, show one crest. So the wavelength is the distance between each wavefront. These are the wavefronts from one source, and these are the wavefronts from the other source. And in the medium, as they proceed, there will be points where 2 crests meet, here, here, or here. The midpoint between 2 crests for each would be a trough. So this point here exactly would be where 2 troughs meet. This point over here would be a crest from one wave and between 2 crests on the other wavefronts. So that would be a destructive interference point. Likewise, this is another destructive interference point. That one right there is a constructive interference point. So what happens as these wavefronts reach the screen over here, there will be points where they always interfere constructively, and there will be points where they always interfere destructively, which forms a pattern. So this point labeled 0 here is right across the midpoint of the 2 sources. The distance of that point to the 2 sources is equal. Point labeled number 1 is what we will see as the next constructive interference point. Point number 2 will be the next constructive interference point. There will be a dark spot if this is light between 2 and 3, and 3 will be another bright spot, and so on, and this goes on either side. This is what we call an interference pattern. So before we explain how an interference pattern works, we have to define a concept called path difference. Any point on the interference pattern is at a certain distance from source 1 and source 2. The difference between these two distances is called path difference. Let's take two sources A and B. Wave from A reaches point C and wave from B reaches point C, and you see that they meet constructively. Point D, however, would be a point where they always meet destructively, because this is a point where a crest will always meet a trough. Point C will be a point where a crest meets a crest or a trough meets a trough. So point C will be a bright spot. Point D will be a dark spot. That's for light. For sound, point C would be a loud spot. Point D would be a quiet spot. Let's explain how this works on this diagram. So back to our interference pattern we saw earlier. On my screen, I measured the distance between two wavefronts as 0.8 centimeters. That's source 1 and that is source 2. We're looking at point number 1. That's the path of point 1 from source 1, which I measured to be 12.1 centimeters. Its path from source number 2 is 12.9 centimeters. The difference of those paths is called the path difference, which in this case calculates to 0.8 centimeters, which is 1 lambda, which is the path difference for the first constructive interference. See the pattern here? First constructive interference, path difference is 1 lambda. Let's see another point, same wave. Let's look at number 2. The distance from source 1 is 12.0, distance from source 2 is 13.6. Path difference is the difference of those two distances, which in this case is 1.6, which is 2 lambda. Well, guess what? We're looking at the second constructive interference. So to conclude from this, constructive interference takes place at any point on the screen where path difference is an integer multiple of lambda, where lambda is the wavelength and n is the order of the maximum fringe. Fringes are each of the bright spots or dark spots. Each region is named a fringe. N is an integer starting from 0. 0 is for the central maximum, where the path difference would be 0 because the midpoint would be equally distant from both sources because of the symmetry. So 0 lambda, 0 path difference is the central max, and the first maximum would be path difference 1 lambda, second maximum would be 2 lambda, etc. We see this given in topic 4, data booklet formulas as such. Now let's take another point. Let's take that point right there, which is not labeled, but it's the midpoint between the central max and the first maximum. That is actually the first dark fringe. We'll do the same thing, measure its distance to the two sources, take the difference of those two distances, which now is 0.4 centimeters. Our wavelength is 0.8 centimeters. This path difference actually measures to be half lambda. For the first destructive interference, path difference is equal to half lambda. Let's take another point. This is now the midpoint between first and the second constructive interference point, which would be a destructive interference point. So if this is light, this is the dark spot. Its distance from one source is 11.9 centimeters, and to the other source it's 13.1 centimeters. Path difference calculates to 1.2 centimeters, which is 3/2 lambda. So for the second destructive interference, we have a path difference of 3/2 of lambda. So we conclude that For destructive interference points, where lambda is wavelength, n is the order of maximum, path difference is equal to n plus half lambda, where n is an integer, 0, 1, 2, etc. So that's how it's also given in the data booklet. Moving on, to show you an example on this pattern, constructive point, that's the central max. Those are all the constructive points. So for light, they would be bright spots. For sound, they would be loud spots. In the middle of each, we have destructive interference points. So for light, you would see something like this. And for sound, that would be the pattern you would hear. Actually, if you have stereo speakers, you connect them to the same source, start a constant frequency, I'm sure you can find on YouTube, generate a constant frequency sound, put the speakers close to each other in an edge of a room, as far away from the speakers as you can, walk across your room and see if you can observe a change in the intensity of the sound you hear. So you put the speakers close to each other at one end of the room and walk across in the opposite end of the room and see if you can observe this difference at some loud and quiet points. There should be no one in the room. There will be reflections. There will be furniture in the room, obviously, so there's going to be some interference with the reflections as well. It's not going to be perfect, but see if you can observe this in a big distance as you can. So let's see what affects this pattern. If we move the screen further away, let's say these are the two sources and this is the pattern that is being formed. If we're looking at a screen that is at that distance, you can see this would be one interference point that is a max, crest, crest, again a bright point here and another bright point here. If you move the screen a little bit away, you will see that on the pattern, the distance between bright fringes increases. If you look even further away, that distance increases even more. So the separation of the fringes depends on how far the screen is from the two sources. What happens to the pattern if the sources get closer? First, I'm generating waves at that separation. You can see how close the fringes are. Clear the waves, and I'm moving the sources closer together. Observe what happens when I start. What we see is that the fringes actually moved away from each other. So instead of more lines that we saw in the region between them, now we see less lines. They have moved away. What happens to the pattern if the wavelength decreases? This one is to show the effect of wavelength on the pattern. So first I will generate wave fronts with a certain wavelength, changing nothing but the frequency. When frequency increases, the wavelength should decrease, and we see that. You should obviously see that there are more points of meeting actually, because the wavelength is smaller, so there will be more wavefronts in the same space, which means more meeting points, more interference pattern lines that form in the same region. Here's a closer look at waves to understand path difference. See how the waves interfere and reach this point on the pattern. This is 0 path difference, and when there's a half lambda path difference, that's where the waves interfere destructively. Taking a look at the effect of slit separation. Further slits cause closer fringes, and closer slits cause further fringes. Looking at the effect of wavelength, a smaller wavelength causes closer fringes, and a larger wavelength causes further fringes. Lastly, listen to the interference with sound. So, how does this work? This is from your textbook, and this is the formula from your data booklet, but this needs some explanation, so here we go. Let's explain the small angle approximation. Here I have a right triangle. I want you to focus on this angle right here, where that's the hypotenuse, the opposite side, and the adjacent side. What happens to the opposite side when I decrease the angle? The angle got smaller and the opposite side got smaller. Let's go even smaller. Even smaller. So you should see that as the angle gets smaller, the opposite side gets smaller and smaller. So when you calculate the sine of the angle, you write opposite over the hypotenuse. When you write tangent of the angle, you write opposite over the adjacent. In either case, as the angle gets smaller, you should see that the sine value and the tangent value should also get smaller. Now, I want you to take your calculator and calculate for an angle of 10 to the minus 5. Calculate the sine of this angle and the tangent of this angle. Pause the video, do that, and you will see that these are all equivalent, because if the angle is small enough to be close to 0, the angle, the sine of the angle, and the tangent of the angle are said to be equal to each other. This is the small angle approximation. Deriving the two-source interference formula. Now, this formula is given in the data booklet, where S represents the distance between the two consecutive fringes, like the distance from one bright to the next bright. Lambda is the wavelength. Capital D is the distance between the sources and the screen. And the small d is the separation of the two sources. So let's say the two sources are d distance away from our screen. So that's the distance between the sources and the screen. As I said before, the separation of the sources is d. And let's say the central maximum is here, where path difference equals 0. So this is the central max. The first max, where path difference equals 1 lambda, say this is the first maximum. Symmetrically, there will be one here where path difference is also 1 lambda. That separation is given as S in our formula. So now I'm going to draw lines from the two sources to this point to figure out the path difference on the diagram. To show the path difference on the diagram, we need the difference in lengths of these two green lines. Since the distance d is infinitely large compared to the distance small d, we can assume this is a very small angle, and due to the small angle approximation, they are almost parallel. So we're going to assume that they are parallel. To find the difference between their lengths, I'm going to draw a perpendicular line from one to the other. So after this point, the lengths of these lines can be said to be the same, which means that distance right here is the path difference, which is 1 lambda, because we're looking at the path difference at the first constructive interference. Now I'm going to label that angle theta, and let's write an expression for the sine of theta. Since that is a 90-degree angle, sine theta becomes lambda over d. Right. Now I want to relate the s and the d to lambda and the small d. So I'm going to use the triangle that s and d make right here. Now using this black triangle, that angle happens to be equivalent to the angle over here due to the small angle approximation. Now I want you to write an expression for the tangent of the angle using our new triangle. It happens to be tangent theta equals s over capital D. Due to the small angle approximation, we know the angle is equal to the sine of the angle, also equal to the tangent of the angle. So using the expressions we wrote before, if you rearrange this, you will find that relationship as given in the data booklet. Okay, that's it for today. Your homework is pages 190 and 191 from your workbook. And I also suggest that you do 4 multiple choice questions from recent exams. The first one is on this slide. That's the second one. The third, and the fourth. I put the questions here so you don't have to look for them. You can solve from the screen. The solutions of all homework questions will be on my next video. Thank you.